Alright, these would be the circular motion banking angles recorded notes. It'll be talking all about us not slipping on curves, which a bunch of y'all need to know about because you go around curves too fast. Alright, this should be quick. Let's imagine that you're riding in a car going around a curve. Sitting on your dashboard is a roll of duct tape. As you go around the curve, the tape moves to the outside edge of the car. Let's watch. It appears as from the passage from your view that the tape is moving outwards and it would go flying out the window. But if we're actually looking at the path of the tape is really a straight line motion. And the car is almost like turning underneath it. So that's the thing to remember is that objects always stay traveling in a straight line path unless acted on by an outside force. So the tape really just stays in a straight line motion while the car is being acted on by the force between the tires and the road. So the car is changing directions, but the tape itself is staying in a straight line path. This is an example of Newton's first law. So when we're finding the maximum speed for negotiating a turn without slipping, meaning we're not going to go flying off the road into like a fence or whatever, we would have to remember our information about static friction. And friction is found by doing the normal force multiplied by the coefficient of friction. And we've got our car on our flat road surface, and our turn has a certain radius. So we can look at it from the side view here on the left, or we can look at it from the top view over on the right. But really, your centripetal force moving to the center has to also equal your static friction, which is moving towards the center. So the car is on the verge of slipping when the FC, or the centripetal force, is equal to the maximum force of static friction. Well, some formulas that we need to recall, so we're going to set these two equal to each other, is that our centripetal force is mass times velocity squared over r. And our friction force is mu times mg. So we would have our normal force being mass times gravity because we're on a flat surface. And our mu would be our coefficient of friction. So we can then take those two formulas and set them equal to each other. And so again, if we do that, then our formula will now look like, well, we have our mv squared over r and our equaling our coefficient of static friction multiplied by our mass times g. Well, we have mass on both sides, so we're going to be able to cancel that out. And so if we want to find velocity, remember we're looking for the maximum speed, then we want to solve for v. And when we do that, we would have v equals the square root of our coefficient of static friction multiplied by our gravity multiplied by our radius of our curve. So this is for, again, the velocity for the maximum speed you can negotiate a curve without slipping or sliding off of it. So let's talk maximum banking angles. So instead of the road being flat, it might be more at an angle. And this is actually, if you've ever gone to a racetrack, you'll notice that they're not flat. Racetracks aren't, like NASCAR racetracks are not flat. They actually have curved, their curves are banked at an angle, so they're at an angle. And that's because they want to be able to negotiate it, and they want to be able to use the weight of their car to provide the necessary centripetal force so they don't have to deal with friction. So they put it at an angle so that they can use that value instead. If they're going too slow on a banked curve, then the friction actually brings you out. You move to the top of the curve. If you're going too fast, the friction will actually bring you towards the bottom of the curve. So believe it or not, most of the time what race car drivers do is they go into the turn high and come out low so that they can go in at a faster speed, and it will actually bring them downwards as they're going faster friction low. But if we don't want to worry about that at all, if we don't want to worry about friction, we're going to make sure that our static friction goes away and it's zero. And if we do that, and because we're at an angle, we have to think about our forces on an incline again. Okay? So when we think about our forces on an incline, we have this angle down here at the bottom of the incline that we've talked about. But we talked about the component factors where we had our value here, this f of gy was equal to our f of n. Well, then this theta was the same. And then we had this value. Well, if we just rotate this, if we rotate this particular, this particular triangle, it will then become this triangle. Okay? So it's kind of a different way of looking at it, but it does allow us to set up some equations. And by applying Newton's second law and what we know about component forces, we can say that our f of x value would equal mass times the centripetal acceleration. And then we would say that our, so we could say our f of n sine theta, because we're really talking about this force right here. This is my f of x. And my f of n sine theta, and then would equal my mv squared over r. And then my f of y would be 0, because we don't want there to be any friction. So we don't want any of that to be going on. We want our f of y to cancel out with our weight of our car. That was it. Because we want to be able to use the weight of the car. So it becomes a part of the component. So that would be our f of y for up here. So this is now our f of y value. So it would equal our weight force, so it would take it out of the equation. So we could say our f of n cosine theta would equal mass times gravity. Okay, so we can say those two. But again, we don't want them to be, we don't want it to be a part of the centripetal acceleration. So we'd be able to take it out. So the sum of it would be 0. They would equal each other. Maybe I should say that. So on my banking angle, moving forward again, I can say that my x value was my normal force sine theta equals mv squared over r. And then I could say my y value would be my f of n cosine theta equal to my mass times my gravity. Well, we saw these similar when we did our conical pendulums, and I talked about those. And so if we divide those two expressions by each other, we end up with this. Tangent theta equals mv squared over r over mg. So we can cancel out our m's, and we end up with tangent theta equals v squared over gr. So that would give us, then we could take the inverse tangent to actually find our angle. So that would allow us to know how fast we can negotiate those turns, what angle we should bank them at if we want to go certain speeds, how far away from the center we should be. There's lots of information that can be used to then calculate how we can negotiate curves better. A lot of this goes into play when we're when they design the large overpass roadways and they're real curvy. You'll notice sometimes that they seem to be leaning, and that's because a banking angle has been built into it. So, just FYI. We will do some examples in class and talk a little bit more. Make sure that if you have questions over notes, you're bringing them and we can discuss them at the very end of class. Have a good one.